So the mean of this workshop is, as the name says, is very straightforward, component separation by means of lifetime. So I suppose in the last days, you have seen a lot of applications of FLIM, different ways of measuring FLIM. And FLIM, in the end, what is good for after all these days? I think FLIM, it's useful for a lot of things, as you have seen. But today, we're mostly going to concentrate ourselves in the multicolor imaging part. So traditionally, we can, for example, use a cell that has either a GFP or either an M-cherry and be able to observe two proteins at the same time using two different detectors by the means of the spectral differences. So this is one characteristic of the fluorophores, that they have emission and absorption spectra in different wavelengths. But it's not the only characteristic of fluorescence. The lifetime, it's also another important characteristic. And what we will try to do today is to separate the dyes, not by the spectral difference, but only relying on the lifetime. So I think you already, let's say, know how to measure, I'll say you have seen many times how to measure FLIM in this by TCSPC, by time correlated photon counting, and it's in the time domain, but I will anyway refresh it a little bit. So we will use a pulse excitation, and for each pulse excitation, we'll try to have one fluorescence photon detected. We will repeat the phenomena n number of times to obtain a lifetime decay histogram, which then will give us the lifetime of our sample. So the process is repeated, and you can see in this nice Wikipedia animation, the detector below that's detecting the photons, and then you have these two histograms here. And here you have the two histograms. One is a log histogram, and the other one is a linear histogram. And you can see how over time they build up to form the decay histogram that we're looking for. So traditionally, the decay then is fitted with an appropriate fitting model to extract the lifetime value. You have already seen, so what it means, an exponential decay fitting. So it's the classic analysis method. It's a very reliable, and it's been useful for many years. And it's very appropriate when you have an appropriate number of photons. But the thing what does it mean, an appropriate number of photons? So as a rule of thumb, it's not always the case. But as a rule of thumb, if you want to fit reliably one component, you need at least 100 photons. Two components, you need at least 10,000. And three components, you need 1 million. So you can see the more components you add, the bigger order of magnitude, the number of photons you need for a reliable fitting. And also then it comes the question that many users that are new to FLIM ask me. So which model should I use? Because, for example, the two exponentials and the three exponentials fit very well my model. But which one is the one, let's say, that is more biologically referent? And this is sometimes tricky questions, because then you need to see your experimental settings. You need to see, for example, in FRET or with other dyes, what is the lifetime of the individual dyes, where are you trying to separate, where are you trying to interpret? And this can be quite tricky. That's why today, for the multicolor separation, I will only be relying on what is called the phasor plot analysis. And I want to stress that as opposed to the decay fitting, it's a non-fitting analysis method. As it has been already very well presented in a presentation on Tuesday by Dr. Gupta. And what does it mean, non-fitting analysis methods? It means that we will just apply a mathematical algorithm that will give us a result that then we will be able to put in the phasor plot. So meaning that, for example, for the same FLIM data, will be today, tomorrow, or in 10 years, the results that you will get with the phasor plot analysis will always be the same, will not change. As opposed to fitting, that sometimes it can change depending on the model, on the software that you use. The different changes in phasor, this will not change. And one nice thing about it is that it's also accurate and reproducible with results just over 100 photons. So you don't need, let's say, more than 100 photons just to get a really good approximation of the lifetime difference. Of course, it has its drawbacks, that it's not as precise as fitting. And it was difficult to use in the past since there were not so many commercial software available. And also one other, let's say, big drawback for some people of the phasor plot analysis is that you can only see the mean lifetime that you're looking for. So you cannot, so the result in the phasor plot cannot be separated in different components. So as you know, if the lifetime of the sample that you're using is more exponential, the dot here will be on the universal circle. But if the lifetime is more complex, it will be inside the universal circle. The problem when it's inside is that you can only say that the lifetime is complex, but you don't know how many components compose this complex lifetime, 2, 3, or 4. And this is something you cannot really extract with phasor data. But we can do different interesting things. So just to quickly remind you, for example, this is a FLIM analysis using phasor. So we have our time decay here. We do a Fourier transform just to go into the frequency domain. And then this way we can extract two coordinates that we'll place in the phasor plot. And with the vector that goes from the origin to our dot and the angle, we'll be able to extract the lifetimes. So in practical terms, we can see here, for example, cell that has been transfected with two different proteins. One is just a free M-cerulean, and the other one is an M-cerulean that is linked with an in-venous high link. So that means that it's a positive Fred sample for this couple. So you can already see here, just by the decays, the lifetime decrease to the Fred. And when we import, when we transform this data into phasor data, you can already see here the two dots have already moved, meaning that explain these lifetime changes. And here you can see the results of the cells. So the free Silurian cell has, of course, a higher lifetime than the one that has the high range. And I cannot see the chat in the moment, so if there is any interesting questions, if someone can take over. Okay, so as this already said, so for single lifetime species, the lifetime are displayed all over the universal circle, and for multi-lifetime species, the lifetime is different. And also one interesting thing about the phasor plot is that the lifetime representation here is not in a linear scale, but mostly in a logarithmic scale. And here, for example, you can see the Rose Bengal that shows an exponential lifetime that is different in different solvents, as you can see here. So it's always more exponential, but you can see how it changes and how this log scale evolves. So the thing is, how are we going to use the phasor to do this separation? So what we're going to rely is in the difference of the lifetimes that we're using. So what we're not trying to do is that we will not try to extract the exact lifetimes of the components we're using. We're just going to quantify the difference between. And as you can see here, for example, if I have a species 1 here and a species 2 here that have very different lifetimes, if they are in if they find themselves in a medium where there are, let's say, mixed, then we can trace here a line, and the components and the mixing components will be found here in the middle between these two species. So you can see here, for example, in the middle, it's a mixture of species 1 and 2. And this not only works with exponential lifetimes, it also works with complex lifetimes, as you can see here. And here is just a practical example of a solution that contains M turquoise and M cerulean alone, and then different ratios of both proteins. And you can see how the proteins having different lifetimes by just changing the ratio. You can see how this dot migrates in a line between both of them. So I'm just going to quickly present you the microscope that it's going to use today. So it's a newish FLIM microscope at the BMC. So newish because it arrived in December last year.
Mariano, just sorry I'm interrupting. You said about the question, you would like to address a question that's in between, or you would like that actually to do that at the end?
I will say it can be in between. It's a workshop, so I'm not really.
Okay, so maybe that I can read two of them. So I don't know if you see the chat or not.
I just opened it. So
okay, good. So then we have one from Thomas and the other one from Sabine.
Okay, I don't see the one from Thomas. So
it's that as you have to transform the time domain to the frequency domain, is there an advantage to directly measure the frequency domain if you would like to use phasor plot?
Yeah. Well, I think I saw that Gerard already responded to that question. It's exactly you have one transformation less. So meaning that you don't have to do the Fourier transform from going to the time domain to the frequency domain. Since you already have the frequency domain data, you can just translate it directly into
okay, good. And the second question from Sabine is that what is the minimum we can resolve in the phasor plot? Here you could differentiate fret and non-fret state. So about 0.2 nanosecond is still possible to resolve.
0.2. I'll say I will mean that these questions. So I've been able in the past to do it, to resolve very different, I would say very little fret differences. But something that you also need to take into account is the population, the fret population that is already fretting. For example, if you have a very little fret, and this fret population, it's only 1% of the 99% donor available, most of the photons that you will get will be mostly from the donor. So you need also to take into account these imbalances, so the ratio between acceptor and donor. Because even with little frets, you have really, let's say, a good ratio between acceptor and donor, you will be able to do it in the phasor. But to be completely honest, it's been some time that I haven't been so many little difference, but I think, yeah, it should be possible.
Good. That was only these two questions, so I think that from now on you can see the chat. And
yeah, I just opened it.
Perfect.
Okay, so now Stefan also is going to help me to present this new microscope. So now I'm just going to quickly over. So it's a very, let's say, nice microscope. As you can see, the complete list is 26 pages long when we receive it. So we can measure the lifetime of any dye from 100 nanometers to near IR excitation. It has available multi-photon excitation from 680 to 1300 for FLIM. It has performance detectors for multicolor and also for multiphoton and also normal confocal lifetime imaging. And most importantly, it has the phasor built-in option that will ease up with analysis. So we're just going to do now, if I can get out, yeah. Tour, so I'll just stop sharing the screen, and I will switch off to the other camera, so let's see. Yeah, so Stefan is going to show a little bit how the microscope is working. So we can see it. So I'm here. Yeah.
So as you can hopefully see here, this is this workstation with two monitors. But in this system, both monitors are coupled to the same computer, and it's actually just one big window screen. The only reason we have two monitors is that we have so many windows that one monitor would be not enough to edit.
Yeah.
And then we have an operator sitting in front of the microscope. And we walk over here.
Yeah, so I don't know if you can hear Stefan, but here you can see the actual microscope. So it's an inverted microscope that has upright, yeah, sorry, upright microscope that we have the options to have, let's say, classical objectives plus change to a very nice 20x objective 1NA water immersion. And you can see on the right immediately the dive module that in our case we have equipped with 3 SMD IDs, so 3 ID detectors that are able to detect for lifetime detection and 1 PMT. So that is very nice. And the internal detectors, let's say in the confocal head, we have 2 SMD detectors, so 2 IDs that are FLIM capable, 2 PMTs, and 1 ID that is not, let's say, properly FLIM certified by Leica, but you can still do FLIM with it, just with lower count rates. So half of the FLIM capable IDs. So this is just the front part of the microscope. And as you can see, we have this curtain system because since it's multiphoton security first. So yeah, it can be a little bit, it's not so practical, but it works. So as long as it works, that's okay. And maybe you can see here behind. So we have just the multiphoton laser just behind. And then you can see all the electronics and all the cooling, hopefully, for this microscope. So as you can see, it's a very complete yet very complex system that we have here. But it allows us to do very nice things, as you will be able to see soon. Okay. I'm back to sharing the screen. Yeah, it's always okay. So we also have another microscope that you will see later and will present to you later. That it's also a FLIM microscope. This time it's inverted, and it's coupled to a STED module, which will give us the possibility to combine FLIM with STED, as you will see in the next one. Okay, so with all of this, I think we will go to see the first sample that I have here. So the first sample that we will observe has been prepared here in the facility. And just to point it out, all the samples that we have observed here are fixed cells or fixed tissues that have been prepared in the facility. So the first sample is a UVX cell line that we have labeled Tom20 with oh no, it's not a Aberior Star. I made a mistake there. So it's a Leica Fluor 647. And together with the phalloidine that is tagged with the Atto 647N. You can see also the parameters that I have been using. So very low laser power and only just one detector. And as you can think, Atto 647N and Alexa 647 are not really possible to separate spectrally. But on paper, they have a very different lifetime. So we'll see if we will be able to separate these dyes. Okay, so we're going back to the Leica window. And I would like to turn off the chat now. Okay, now we need to close the curtains. Okay, so as you can see here, I'm using very little laser power because the labeling is really good itself. So, okay, let's go. I have just one detector. I think I will just this big so people can see it better. Okay, so I'll just give it a go. Okay, my stuff has moved a little bit. Okay, so I have here, let's say, just a normal confocal menu that people that have an SP8 or an SP5 are already familiar with. So I don't have the lifetime information displayed here. I have it in the screen on the right side. But I will show you to do that later. For now, we'll just take a lifetime image. So the format, it's just the format recommended by the microscope to obtain a Nyquist. So to obtain the best resolution that we can get from the sample here. So in this case, it will be 640 by 640, and it will have a speed of 400 hertz. So having one frame is going to take me roughly a little bit less than 1.5 seconds. I'm going to repeat the process 30 times, so more or less 45 seconds. So here you can see just the normal fluorescence image that is being built up. And once it's finished, I will switch to the FLIM part to try to unmix these labels. But something that you can already see here is that, I don't know, by eye, it's kind of difficult to differentiate where the actin is and where the mitochondria is. Because these cells have the particularity to have very deep, very stretched mitochondria that are also filament-like. So it's not so easy to differentiate from the actin just by the eye. Okay, so it's finished. So, okay. Sorry, now it's better? Okay. Yeah, sorry about it. Just we have a very heavy background removal tool, so okay. So now we took our FLIM image. Now let's go to the FLIM menu over here just to analyze it. So okay, so it's the same image that we acquire, and there is already two things or three things that we can see here. The intensity-based image here on top. Here at the bottom right, we can see the lifetime histogram. So we're using a repetition rate of 20 megahertz to do this imaging, hence the 50 nanosecond window. So we have a really nice lifetime decay until the end. And here on the left, we have something that is called the pixel intensity histogram. So this is a Leica specific tool to know that we are acquiring with an appropriate photon flux. And we're not that we are not acquiring too little or too much. So in this case, we have roughly up 0.9 photons per pulse. And normally the maximum that we should more or less acquire is 1 photon per pulse. So we should try not to exceed that one, because then the photons will be more or less put away as it is in the Leica software. So when you have, let's say, too many photons, you can run in other problems, so they can be just put it away. So in this case, we're good. And now let's see what the fast FLIM image looks like. So as I told you, the fast FLIM image is just one of the images we can see that, let's say, we already acquired with the lifetime data. And you can already see very colorful image here. They are symbolized by the two dyes, and maybe you can see the mitochondria and the actin a little bit better. So just let's play with it. And here you can see, I think, for FLIM measurements, when you're doing a FLIM measurements, the detector goes automatically in counting mode. So standard mode is not used anymore. So if you're doing FLIM, it's already in counting mode, so you should not worry about it. So you can already see here the nice two colors just with the fast FLIM image. Of course, it's not perfect because, yeah, I will say the thing is that now I'm just playing with the color display here. And of course, yeah, you see, it's very, I don't really have, let's say, a graphical representation to, no, I'm not using, that's the thing, I'm not doing a fitting. So I'm not using a calculated IRF, and I haven't took a reference before. This is just the lifetime differences of the dye. And that's the beauty of it. These two dyes have very different lifetimes, so they can be really used for this. And okay. So something here, as I told you, with the fast FLIM analysis, yeah, it's kind of difficult, let's say, to more or less define the colors, especially when you really don't have a good reference. So what normally can I do, traditionally, it's do a FLIM fit. So I can just flip the fitting the overall photons in the image, and then trying to apply the same model to each pixel. So roughly here on the brightest pixel, I have just over 1,000 photons. So it's not really that much, but just let's give it a try to see what fitting looks like. Okay, the first non-exponential fitting was horrible. By exponential, also not great. I think it was, yeah. Three exponentials, it kind of works better for exponentials. Yeah, chi-square 1.2, so seems good. So I will just try to apply this model to my whole image to see how it looks like. Of course, I can choose also in which pixels do the fitting, so I don't waste my time on background pixels to say this. So, okay, I will say exclude all the pixels that have, let's say, 20 photons. And the lifetime will be fixed. So the only thing that will change is the amplitude, meaning the ratio between the different lifetimes to be able to differentiate. So I'll just go for a fast fit here. And here you can see already the 3 channels. And you can say it works okay-ish. We can see some color separation, but it's not really as great as I expected. And also the problem is that we have here 1/3 components, and we're losing photons in this one that are not attributed to any of our dyes here. And we can still here see some crosstalk in the green channel. For example, here in the red channel, we can see the actin very nicely, and we can see also some actin crosstalk in the green channel. So let's say it works nice, but it's not ideal. So for the results, let's say I will discard this component because it's mostly noise. And if I put them together, yeah, it's not a very bad result. But I think I will just change the colors because I don't really like this. Magenta, I like the magenta and green. Got it. I will just adjust the look a little bit. And you can see it looks kind of okay. But we can do much better with the phasor. So going to the phasor, you can see immediately this big line here. So as I told you before, these dyes have 2 different lifetimes. And depending also on the intensity, the intensity of the population will change. So we can see, for example, that the actin lifetime is longer than the Leica Fluor 647. So we can see the lifetime more on the left side of the phasor, whereas the Alexa Fluor has a shorter lifetime, and it's on the right side of the phasor. So what I have done here is just choose roughly 2 rows in the phasor plots, and here you can see the results in colors. So what this row do is that all the pixels, or all the, let's say, the coordinates that are here, or all the photons that are, or the pixels that are here, will be colored in the color that is inside the row. So for example, if 1 pixel creates a coordinate and it's placed here inside, it will be turned red. If 1 pixel has coordinates that will put it here in the green part of the row, then it will be color green. So you can more or less approach the phasor plot as a fax plot. And this is something that talks more to biologists that I work with that have done fax and cell counting. When you told them that the phasor plot can be just used as a fax, then yes, I will say it's in more practical terms, because here what we're seeing is just difference in the populations in the lifetime. We're not really interested in the lifetime itself. So how do I decide the radius of each roid? So I decided according to the size of the, let's say, of the size of the phasor, let's say, dot that I see here. But I mean, being let's say over, as you can see, I can make it as big as I want, but it will still not color the red part, as you can see here. So I mostly decided based on what I see. So it's a very empirical approach, this one. And as you can see here, it's also prone to artifacts, because here we have just a 1-0 response. It means that if a pixel is inside the row, the red row, it will turn red. And if the neighboring pixel is inside the row, the green row, it will turn green. It makes very, let's say, sharp differences, and we don't have, let's say, a smooth transition as it will be desirable. Okay, yeah. So what happened to the pixels that contains signals from both fluorophores? That's a very good question, because here we have a lot of overlapping structures. So what happens is, as I showed you before in my presentation, and maybe I will, is that we have the pure lifetime of the dye here on the left, and the pure lifetime of the other dye here on the right. And any pixel that contains a mixture of both dyes will be here in the middle between both of them. And so you see all this trail that you see here in the middle corresponds to all those pixels that have a contribution from both dyes. Yeah, exactly. I would say it's a bigger intensity for red, and yeah, you can expect, like, it's a bigger radius. But the problem with these methods, I told you, is that we only have a on-off response. So it's not the one that I really use. What I use, it's this little tool here that we have here. So what I'm doing here now is that I just have a color bar, and I will just make it big enough to englobe all the pixels that I see. Is that the color bar will color the pixels depending on the lifetime, and here we will have mostly a gradient. So depending on the position in the phasor plot, it will have a different color. And then in this case, all the pixels that contain both dyes will also show another color depending on this ratio. Of course, it's very, let's say, difficult to get something from this image now that we are, let's say that we have this rainbow look here, but we can change it. And for example, let's say I just want to see the mitochondria. So I just put a weight. So I just want to see the mitochondria. So now what this bar is doing is that all the lifetimes that are long, here on the right part, I will try to zoom in a little bit. Yeah. We have a gradient from black to magenta. So we have an intensity gradient depending on the lifetime of the dyes. So the closer the dyes are to the pure form of the Alexa fluor, the brighter they will be. And the pixels, the closest to the Atto 647 in lifetime will be just darkened. And you can see here the difference. So here we can see the mitochondria, and I think you can already see it better in this case. Okay, I will just have now with some questions. Not really, I'll say, do I have to use control of individual dye samples to see where these populations are located? No, in this case, no. I don't need any control or individual dye samples because I'm using the phasor plot, and as I told before, I'm only interested in seeing the difference in the lifetimes. So I'm not interested in seeing the pattern. So if the lifetimes are different enough, this difference will be reflected in the phasor plots. And we will use this difference to just separate them. So how did I switch from magenta to rainbow? So you have an option here. I don't know if you can see me. I will say, so you have, yeah, you have an option here where you can choose which color to color your, so you can go from rainbow, that is the original one that I don't like, to the magenta. And then you can adjust that as you wish. So yeah, in this case, I choose magenta. And now that I did for the mitochondria, I can also do the same thing for the actin. So in this time, I will apply just in another color. So I have already the rainbow one, and then I will just switch it to green. So we'll go from black to green. And here you can see we have the actin contribution without the mitochondria. So this is the original raw data. This is the actin only, let's say, live tag, and this is the mitochondria only labeling. And now what I can do is that there is no easy way so far to do it in the Leica software. So what I do in my case is that I just save this image as, let's say, from 21, let's say. And then I save this image as actin image. And then I go back to the original, or say to the other Leica interface. I do an overlay of them. So now I have, okay, this didn't work. For some reason. Okay, I will try to make it again. Okay, I forgot this save phasor mask. Yeah, so not as straightforward as I wish to. And it will be nice to have a more smoother workflow in the future. Okay, so let's go again. Acting up. 20. Let's see if now it worked. Yeah, it worked now. So now I will overlay them. And here we have our overlaid image, lifetime separated. And some nice thing is that you can see here on the overlapping structures, the separation works really good. To be honest, it worked better than I expected. So for example, the case here that we have mitochondria going under the actin, and we can see here how this mitochondria continues, goes under the actin and then continues its path. Okay, now we'll just ask, okay, how big is the difference in this case in lifetime? In this case, the difference is pretty big, so that's why it works really well. So we're going from a lifetime roughly from 3.4 to 1.5 nanoseconds between the two dyes. So I assume the Atto 647N has a 3.4 nanosecond lifetime, and the Alexa 647 has a lifetime of 1.5 nanoseconds. So roughly a 2 nanoseconds difference. Okay, it's possible to get the raw measurements as an image and do custom analysis of a file landing. I think, yeah, it's possible. I mean, you can take any lifetime image here in the Leica software, and you can just export raw data, and it exported as a PTU file. And then PTU file, it's, let's say, the Picocon classic file, but there are many tools to analyze the data. Can you do this with more than 2 colors? This is something that you will need to stay tuned, because it depends how do you interpret 2 colors. But let's say we've been working now, because now these 2 colors work very nicely, as you can see. So we have, literally speaking, just a bonus. So in one channel, we have these two dyes that work really nice. And we're working to add a third dye in the same channel to be able to separate the phasor. But this is more complicated than expected, mostly because when you're labeling with antibodies or with other dyes, the problem is that the lifetime of the dye in paper usually changes in this case. So this is something that you also need to take into account, that it's not because on paper the lifetime are different, that they will be different once you label them. And also depending on the structure of the lifetime of the dye can change. So this is something, let's say, that you need to try. But at least with these ones, with the Atto 647N and with Alexa 647, I think it will work in most cases, this lifetime separation. What happens is the difference of the dyes is really small. So half another second. So as I will show you later, I think it's also possible. But then it also depends how much they're overlapping, because one of the main problems you can encounter is that structures are overlapping too much, and then it will be more or less a little bit more difficult to separate it. But I think it will be possible. The problem is I don't really have a control or some label for now, but we can see later. I have other samples, and I think the difference are smaller. Okay, if the lifetimes are different enough, yeah, I would say I think we can discriminate many lifetimes. The thing is, I would say the problem that we're running now, it's not problem, but to find the good dyes that work always, let's say, because doing labelings of 3 or 4 colors it's quite challenging. And also one important thing is that you want to equilibrate these labelings, meaning that since now you're looking at one channel and you're extending with one laser, you don't want one label to be super bright and the other one super dark, because in this case, you will not be able to obtain sufficient lifetimes to be able to separate them. So you need more or less to equilibrate the labeling that we see. So have you tried to separate autofluorescence for fluorescence like this? I haven't tried, but it should be in this case, pretty straightforward. I don't see really a problem. Take into account that fluorescence, autofluorescence have usually a short, either a very short or a very long lifetime. So you will be able to filter them in this case. And I think the other question is, can you remove autofluorescence? Yeah, I think you will be able to remove autofluorescence. Because, for example, if we go back to the phasor plots, and I don't know if in this sample you can see it. Let's see. Wonderful. Okay, so you can see in this part here corresponds to the pixels that don't have much information. So it's mostly background. And one thing that you can do, for example, to just filter these photons is also taking this bar tool and just applying it in this case here. You know what I mean? So in this case, you will also filter the background. So if you have, for example, here a very, very bright, what I would say, autofluorescence dots that correspond to the autofluorescence, other things, you can always tune it down with this tool with grain information. And also one nice thing about the phasor is that, okay, this is a workshop. It works very nicely because I have to the sample, it's very bright. I have roughly how much, nope. Okay, now it doesn't. Okay. Okay, now it's happy. So you can see I have roughly just a couple of hundred photons per pixel. I mean, no, this is the filtered one. Yeah, I have just a couple of hundred photons per pixel. So it's not very much for a lifetime separation. And I can even decrease it more. So it's a very, very, let's say, very noisy image. I just have maximum in the brightest pixel, I have only 42 photons, but the separation still work, even with a very low photon quantity. Of course, the image quality is bad, but you can at least recognize the structures with very, very little photon counts. So this is also the major advantage of the phasor approach is if you have very little counts, you will be, if the lifetimes is different enough, you will be able to differentiate them. Can you also measure anisotropy on this microscope? That will be mostly a question from someone from Leica, so I don't know if, Daniel, you're there, do you want to jump in?
Hi, Mariano, yes, I'm here.
Yeah, so can you
what was the
measure,
question? Sorry, could you repeat that again?
So can you also measure anisotropy on this microscope?
Oh, good question. In principle, yes. So you can add an analyzer filter in the notch filter wheel. So for the internal detectors, you could do that, and then you could rotate that as well, and then simply measure different rotation positions. I don't know if that answered your question.
Yeah,
I think it's on the question from someone else, but I think I'll say yes. Thank you, Daniel.
All right, you're welcome.
Yeah. Okay, so another question is, how do I decide about the harmonic? So the harmonic is, it doesn't really change the data. What it will change is the visualization. So for example, in this case, I have an harmonic 3 because I just want, let's say, to see what the difference. But if I do an harmonic 1, what it will do is that, as you see here, it will shift the lifetimes here to the left. So something about the phasor plot is that the distribution of the lifetimes will depend on the repetition rates that you are using. So the lower the repetition rate, the bigger, let's say, the max value of the phasor plot is. So in this case, with 20 megahertz, you can see that the structure, okay, it's mostly on the right part. I could also use it, but just to be more comfortable, I can increase the harmonic, what will roughly do, I will say, really, let's say, just speaking, is it will divide by 2 this max value. So for example, if I increase the harmonic to 2, you will see that it will shift a little bit more to the left. And if I increase it to 3, it will shift it even more to the left. So the harmonic is just based, it's also, let's say, more or less in this case, empirical. So you just choose an harmonic that you then are comfortable working in for the lifetime differences. Because you need to remember, as I told in the beginning, this phasor plot distribution, it's in a logarithmic scale. So sometimes if you want to see very little, very big differences, you might need to change the harmonic to match the difference that you're looking for. So it's mostly visualization. Okay, and then I'm going now to show you one image that I pre-recorded that I think is very, very nice. So this is one image that I pre-recorded of a very nice cell where I did this color separation. On the left side, of course, I have a lot of photons and I have the higher resolution that I can have. So this is an image that is 1024 by 1024 at 700 Hertz. And it took me, I think, 1 minute to make the image. So you can see very beautiful, very nice color separation. And on the right side is the same cell. In this case, I just took one FLIM image, which roughly took me 1.5 seconds. And you can see the max photon value in the brightest pixel is 48 photons. And even that, let's say roughly in the cell itself, I have between 10 and 20 photons per pixel. So not very much. But I'm still able to see the differences here. And one of the nice things also about it is that if you zoom here, or mostly here, so it's start, okay. So, okay, so you can see here, I just need to change this again. So, okay, these are the lifetimes of the dyes in PBS. So the Leica Fluor 647, 1 nanosecond, the Atto 647N 3.4 nanosecond. So you can see finally in this sample, the Atto 647N with the phalloidine in the actin only changed it a little bit, it's 3.5 nanoseconds. The Leica Fluor, though, increased in the lifetime. We are measuring 1.5, roughly 1.5, as opposed to 1 nanosecond. And here on the right, you can see the spectrum of the dyes. And you can see that, yeah, I'll say spectrally separated would hardly be, I'll say it will be a huge fit, but it's not what we're looking for. It's easier just to separate them by lifetime than spectrally. Here you can see the separated image, the actin, the mitochondria, the image together. And one nice thing about it is that here I did a zoom in part of overlapping structures, and you can see how nicely the separation works. Even with overlapping structures, that is the biggest struggle for unmixing. And I already showed this image to some people, and they told me, yeah, this image looks like it's like being acquired with 2 different channels and just overlays. So the quality that we're obtaining is very good. And it also works the same with the low photon count image. So you can see here on this part here that the overlapping structure still exists, but the color separation still works very nicely, even with low photon counts. And with these photon counts, it will be very, very difficult to do any kind of fitting analysis with it. Of course, it works with other cells. So in this case, this is just some ELA cells that also with the same dyes, from 20 and Atto 647N. So do you have any more questions for this sample? Because if not, I will just go back to the, let's say continue to the next sample. So now we have a 3-color sample, but it's a little bit more complicated than that. Because as I will show you now, it's an ELA cell line that this time we have from 20 Aberior Star 635P. We have the same phalloidine, and this time with Atto 647N. And we have a 3rd color, but in this case in another channel. So we were looking to the far red. Now we have 2 dyes in the far red and 1 dye in the red channel. So the noob with the Aberior Star 580. So the parameters that I did for the acquisition is I did 2 sequences. I did prime sequence where I acquire the Aberior 580 first, and then in the second sequence I acquire the other 2 dyes. So now I will just now proceed to change the sample. Also, in the meantime, you can just ask questions. I will try to answer them later.
So maybe just one thing why we got interested in this in the first place, and that is that people came around and were asking us how many channels can you actually do, and this were people from using usually flow cytometry. And then I was very proud to say that with our confocal we did already 6 different colors and probably could do 7th, and that was before we had the FLIM systems. And then that person said, oh, in flow cytometry we're usually doing 12. So in flow cytometry, of course, you have to be aware that there is this, what they call their compensating, which is essentially channel linear unmixing. And what I don't like about that approach is that you cannot really easily check the results because you don't see the images and how good that separation actually is. But still, they claim they can do it. And if it can be done, then they have, of course, high numbers. So they have good ends to separate these things. So that's what they're claiming. So, and in that connection now, when the FLIM system arrived, I was interested in how many colors can we actually get out of it if we use spectral separation on the one hand, the classical thing, and then also if we can use several different dyes in one of those spectral channels. And it seems that we can improve the number quite a bit. We're still working on it, so we don't have a final result here of what's possible. But definitely we can, in some channels at least, where we have good dyes, we can see 2 or maybe even 3 different dyes labeling different structures. And that maybe also answers Thomas' question here. Besides the theoretical possibility, do you ever have to really stain 2 channels in the same spectral channel? Yeah, and then another reason to do that we may show in the next workshop where we have super resolution stat, where you would like to work with just one depletion laser for several reasons, but that's maybe for later on. One practical problem that we're having in my group now is that usually we're using primary, secondary antibodies. And with so many colors, we're running out of different species for the primary antibody very fast, and which is one of the reasons why we why we like to use actin staining, in this case phalloidin, I believe, because there we don't have to use rabbit or mouse antibodies, because good primary antibodies from other species are not that frequently in use. So usually with our users, at least at this point in time, the limitation is getting the label into the sample and not really the microscopy. This would change, of course, if you would use primary antibodies which are labeled to different dyes. But those dyes used for flow cytometry are often very bad in terms of bleaching under the microscope. So there is probably quite some development needed of getting those dyes then onto the different antibody species, or getting good microscopy dyes on those primary antibodies people want to use. Do I mean combine spectral imaging and FLIM? Yes, of course. So we would have like a green channel or blue channel, green channel, orange channel, near red and far red channel. And in all of those, we would like to have more than one dye to get the maximum number of possible dyes. So Martin suggests to use some antibodies linked to oligos for specificity rather than species-specific secondary antibodies similar to paint. Yes, that might be possible, but again, there you have to do some development. And since we are a core facility, doing the actual research is kind of a side game that we're doing. So we just don't have the manpower to get into it. So I'm hoping for a group here locally, which is interested in getting all those colors, and then they could help us here with the development. So we would do hopefully then the microscopy side, and they maybe would do the antibody labeling here. Mariano, whenever you're ready to take over, please do.
Yeah, sure, no problem. Yeah.
Yeah.
Okay, so I see other questions. How do you deal with the fluorophore aggregation in the very bright spots? I mean, it's a very bright spot. There is not so much you can do about it. You will still analyze it in the lifetime, but I don't know if it will give you meaningful information. I mean, if it's just located in one region, then it's not really, I will say, a problem. It happens in all samples. It will be just analyzed, and it will depend up to you if the analysis makes sense or not. So, okay, I think keep balancing. Yes, yes, that's a very good comment, Hela. The balancing the brightness is very important also in lifetime. Very, very important, especially with overlapping structures. And this is one of the main, let's say, feats that we need to bypass, is to find labeling strategies that work well for the two dyes and that the balancing the brightness between the two dyes is correct. Because of course, if the balance is too big, then you will mostly acquire one dye and not the other. So yeah, it will lead you to very poor separation. Even if I already showed you that you can separate using very, very little photon information, still, I would say the better I would say if you can balance your dyes, then the better it is. Okay, so now we have here 3 dyes. So as I told you, I have the NUP, the nuclear protein from the nuclear pore complexes. And I also have, again, the mitochondria with COM20 and the active label. So one feature that I would like to show you about the microscope here that is very nice is that since we have spectral detectors that we can change the bandwidth as we wish, we can here, for example, use 2 detectors, in this case here, my 2 FLIM detectors, to just aggregate and acquire all the photons from one channel. Because in this case, the labelings are really good, they're very bright. And if I want to acquire even faster, I can just put the 2 detectors together and just pump up the laser power and the brightness. I will say the photons will be distributed across the 2 detectors and then will be unified later. So this is a very nice feature. And in this case, let's say I could aggregate up to 3 detectors if my sample is really, really, really bright. I would say if I really needed to. So that is very nice. Okay, so now I will just again just try to find a nice focus, and I will just launch the acquisition. So as I told you, I have here two sequences. So we will acquire first one channel, then the other. And I just don't need that many photons. And okay, let's go there. So, okay, so this is I'm acquire first the NUC channel, so the nuclear pore complex channel, as you can see here. And then I will acquire the other channel. So we just need to wait a little bit to get that done. Okay, how I combine the two detectors. So I can actually show you even here now during the acquisition. So what I do is that, as you know, in the SP8, you can just change the detectors as you wish. And here I choose two bandwidth of these two detectors. So I just put them one next to each other, as you can see here. And then in the FLIM menu from Leica here, you have one tick box that it's called, apparently appropriately, especially setting. And here you can manually assign FLIM channels. And here you can tell to the software, okay, I want you to make one FLIM channel out of these two detectors. So I'm just telling to the system, please take the signal from these two detectors and assign it to one FLIM channel. So the output will be one FLIM channel. Of course, if you forget to do it, which has happened to me, you can still do it later. You can also have this option here. You still have the semi-specialist setting, and then you can manually assign detectors. So for example, if I wish, I could do a third channel, and I say, okay, this third channel, just put everything in the same channel. Why? Because why not? And then it will aggregate all the fluorescence in all the channels. You can see here. And you can see that, yeah, even if these dyes were overlapping, you can see it kind of work for the lifetime. Yeah, well, not so great, but okay. Now let's go to the phasor plot to see how it looks like. For now, we'll just look at the phasor plot of my, let's start with the dye alone. So here, this is just this is just one dye. So it's my red dye. And as you can see here, I just have one big dot because I just have one dye. And then of course you have some, let's say, difference in the lifetime that will be according to the labeling, background, and other things. But you can see if I go over this dot here, yeah, it's the lifetime of my dye. So here. Interesting. So the advantage is that of having two detectors instead of one is that in this case, my sample is really bright because we're using synthetic dyes. And if I just pump up the laser power, then I will just start to overwhelm the electronics on the detector. So the advantage of putting two detectors one next to each other is that the photon generated will be distributed in two detectors rather than one, meaning that I can acquire more photons, I'll say twice as many photons in the same time duration. So I can just increase the laser power and just say to, hey, I just want to acquire a bunch of photons so I can finish my image faster. So maybe in live cells, you will not find this because for fluorescent proteins and also live cells, it's very difficult to saturate detectors. But when you're using fixed samples or fixed tissues, and you're using synthetic dyes, you can very easily saturate detectors, especially with FLIM. So that's the advantages of the two adjacent detectors windows right on the large one. You can just acquire twice as many photons for the same amount of time. Okay, so this is one dye. Interesting. Yeah, that's what I was actually looking. So to be honest, I haven't really had so much time to do this. And yeah, I would say maybe we can do some lifetime filtering. This one, I will color it. It was yellow. I think it was yellow. Yeah, actually, yeah, you can see that's quite interesting. That's if I want to, so as you see here, this is a practical example of how I can use FLIM to just subtract the background. I really didn't try about it. Of course, I have just some minor artifacts, but I think the result is not too shabby. Okay, so I can reduce the background coming from the inside of the, maybe it's easier to see it in this grayscale. So I keep my fluorescence in the membrane, more or less, and then yeah, but I would say there is a lot of playing around, but I think something can be done. Okay, now let's change to the other one that has our two dyes. So as you can see here, the difference this time is lower with these two dyes. So I will just proceed to do the same thing I did before. Okay, so in this case, I will just up again the actin. So I just will isolate the actin for now. Now I will do the same thing, but oh yeah, no, but I said that this I wanted to see. I'll do the same thing, but with the mitochondria. So up, the mitochondria are here. And then all I need to do is again save the images. So from 22, what we call it this one. This one I will call it actin 2, and then this one, yeah, this is my dye. Okay, this one will just color it a nice yellow. Okay, now I come back to the Leica software. Again, overlay everything. And yeah, have some problems here with the dynamic range. Yeah, it's really, really nice if we can have another tool for it. But for now, I haven't really. So yeah, and here we can see more or less a 3-color image done just with 2 channels. And yeah, I think it looks very nice. Very nice color separation. And of course, I have also some images that I can show you. So these are all some images that I did before for the workshop. So you can see it works very, very nice. I will just change here again. And with some more time, let's say, and some more, let's say, confocal or acquisition parameters, you can see that we can really nicely separate the 2 far red dyes. Then we can add the red dye, which we can also, let's say, filter by lifetime if we can see, because apparently the lifetimes are different. And then we can see the overlay. And I also made a zoom in part of the image where the 2 far red dyes are overlapping. And you can see that the unmixing works really, really nicely. And of course, it also works well with images that have very poor photo statistics, as you can see here on the right. And if we zoom in the overlapping parts, you can see that even in the poor photo statistic image, we can see, or we can more or less differentiate the structures. It's not as nice, but we have some information. Okay, can I do batch analysis? So that is one of the problems, is that as you have seen now, for my phasor analysis, I have mostly done an empirical approach. So I haven't really done any, let's say, value or used any discrete value to differentiate them. I just see 2 clouds and I say, okay, this cloud is one dye, this cloud is another dye, and then I just adjust my parts. And then how do I do it? But I think this will be a nice subject for the machine learning people. That, for example, you can just have a batch of lifetime images and you say to a machine learning algorithm, okay, I know I have 2 dyes here, and please find them. And then, for example, the algorithm will find that will predetermine, okay, this is one dye, this is the other dye, these two dyes are, this line that is in the middle is the mixing of the two populations and will be a mixer. But yeah, it will be actually a very cool application to do this in batch analysis. But so far, at least with this commercial system, it's not possible. Yes, the samples are embedment in multimedia. So which multimedia is, it's either Fluorochromes G or CFM3. Both multimedias have given us very nice results, but the CFM3 has given us lately some bad results. And we still try to determine why it is the case. So we still don't know.
Maybe one comment from me, Steffi, is that, so because I was asking about this because we made the experience that the lifetime is really affected if you use mounting medium because of, I mean, you have all these. Yeah.
Yes, and our experience, it's getting even worse than that because if you have it, for example, in prolong, a mounting medium which is hardening, the lifetime changes over time. So it's a difference whether you measure it the day after you embedded it or a week later.
Absolutely.
So it appears it appears in general that for lifetime measurements, you better use non-hardening mounting media. And the two that we're actually trying right now is Fluorochromes G and CFM3. Yeah. And we're not yet quite sure which one will turn out to be the better at the end of it, but this is what we're trying right now.
Yeah. But just for example, to show you the sample that I showed you in the beginning, the 2-color sample, we prepared it in March of this year. And it's still stable. So this is one of our golden slides that I hope we will be able to use as long as possible.
Sure. Yeah, we actually did the same combination and had the same experience. So but it's so the point is, I guess, if you have smaller differences, so the effect can be dramatic, the change from what is expected for the fluorophore and what is then what you measure in reality in such a sample. Also attaching to the to the antibody molecule, and then just binding to the antigen. So that was our observation. Can influence depending on how stable the fluorophore is. So sometimes almost nothing changes. Sometimes you have a dramatic change.
Yeah, exactly. So that's why I say in the beginning that it depends. It's not because on paper the lifetimes are very different that they will be very different in your sample. Mm-hmm. And the only way to know is to try, because this is the kind of things you kind of more or less take hints from other labs. But I mean, when people say I have done this in ELA cells, there are so many different ELA cells that the same labeling will look different in every kind of lab. So
mm-hmm. Yeah, and of course, about the mounting media, the anti-fading stuff, what is in there, what is sometimes, not known, what's really the mixture of this mounting media could influence, and then you cannot control it very well. So just to keep it in mind.
Okay, so Thomas, can you deconvolve the separated image, the one with low photon counts? I'll say I don't see why not. I think it should be possible. I haven't really tried, but I don't know. Maybe Daniel can answer you that. If you're there, Daniel.
Yes, I'm still there, Mariano.
So can you deconvolve a FLIM processed image?
Well, in principle, of course, you could run it through the deconvolution algorithm. The problem, however, is that deconvolution takes into account the shape of a point spread function. And now, as we're using not the normal intensity-based point spread function, but separate our channels based on the lifetime information, that might actually look different. And it might actually look different in different parts of the image. So using the standard intensity-based deconvolution algorithms wouldn't work, in my opinion. However, if some more development is put into this question, I think in the future that might be possible if we also take the lifetime information into account here.
Yeah. Okay, thanks. Yeah, thanks, Thomas. Yeah. TT-Fluor CFM3 and Fluoromon G are the two multimedials we're using. And we're still not sure who of both, which one of the two of that is the best. Okay, so now that we have done 2 colors, we can say, okay, this is too easy. So now we will try to do 3 colors. And one of the problems I'm running is that now I have too many colors to do an appropriate separated image. So we'll see what happens. So now we'll have 2 colors in the far red channel and 2 colors in a more or less, what we call in this orange channel. So now we'll see the following with Atto 555, the nuclear 4 with Alexa Fluor 568, and the cell line that we will be using is a cell line that has a stable expression of lamin EGFP. So we will use a booster EGFP that labels the Aberior Star 635P, and we'll also use a tubulin staining with Alexa Fluor 647. So we will have all these 4 channels labeled with different dyes that will hopefully be able to separate the different colors. And again, I just did 2 sequences with 2 detection channels, as you can see here. So yeah, so something that I want to message. Oh yeah, something that maybe I wanted to point it out because I didn't do it or I didn't show it in the last image is that since now we're using 2 different dyes, now I can tell you that the lifetime differences between the Atto and the Aberior dyes are lower. So, for example, in this case, to separate the actin and the mitochondria. So in the ELA cells, the Aberior dye has a lifetime of 2.45, so 2.5 nanoseconds. And the Atto 647 has a lifetime of 3.3 nanoseconds. So again, shifted, and in this case, we have less than 1 nanosecond differences. So we have roughly 0.8, so 800 picoseconds difference. And you can see that it still works really nicely. Okay, so now let's go for the bonus sample that we just got this week. So let's see how it goes.
So concerning the mounting media, we have very limited experience with those. So the one experience we had was that prolongs maybe not so good. We've tried that because otherwise we had very good results with stead samples and prolong, but for lifetime it doesn't seem to be a good choice. And then at some other meeting, I was introduced to CityFloor CFM3, which is then something that we've tried. Flow Mount G was something that we had in the lab anyway, therefore we tried that. It might turn out at the end that maybe some other mounting medium is even better than that. Maybe even some self-made Dubco or whatever. At this point, it's really too early to tell what might turn out as a very good, let's call it preservative for lifetime for the different dyes. We just don't know yet. So we have very limited experience with our, we can tell you what we've used and what worked so far, but we can't tell you what would be the best to use. So if you have any experience, maybe yourself, I'd be happy to hear about it.
Okay. Okay, now I'm just adjusting the new parameter for the new sample. So up, 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 up. Okay, let's try to pick up the cell. Okay, now I'm just checking that things are good. Oh. Okay. And I'm just adjusting the laser power just to make sure I have enough power. Okay, yeah, I can even do more. Because anyway, I will just be focusing on this part of itself. Okay. Less. So this is actually a very interesting thing because the parameters that I have noted down are, for this slide, are the ones when I was using the other microscope, the other FLIM microscope. And they're kind of completely different, mostly with the laser power. So that's what I'm telling you. This is why it's so important to, even for these measurements, even within the same lab, different microscopes, different things can change, and we need always to make adjustments and to make sure we're properly doing the physics. Okay. This. More power. Okay, I don't know how good it will be this color separation, but we'll give it a try. Okay, all set. Let's go. Yeah, exactly. I would say every state, I would say every step of fixation, labeling, and all these things will change the dye. Ah, shoot, forgot to change the camera. Okay, back. Okay, so you can see here, I'm acquiring the two channels. So here on the left side, you have this is the red channel. So we have the orange channel. So the Atto 555 and the Atto and the Leica 568. And here on the right, we see the Aberior Star and the Atto 647N. Okay, analysis is done. So now I can proceed by detectors. So here you can already see a classic example of labeling imbalance. So you can see here just one really big dot and just a small trail here, meaning that this dye that has the shorter lifetime has overwhelmingly, let's say, contributed to the image other than the other one. But I think even if it's bad, it's not as bad as you might think. The tricky part is that you will just need to find where your dye is. For example, here. See, up, then I can just recover here. So this is the nuclear pore complex. So this, just for information, was this is the base image. I will say the raw data. And after the unmixing, I think red is not easy to see. You can see it here. So very nice. And now I will do the same thing with the actin, that it should be simpler. So which color did I put the actin now? Okay, so I wanted the following. Okay, this I wanted in cyan. And you can see that works quite well, if I may say. And one of the nice features about it is that, okay, I still have some artifacts from the lifetime separation, but you can see here these actin fibers that are overlapping and going just below all this background fluorescence from the nucleus. It's just kind of filtered. We can distinguish the actin fibers going below. So it is quite impressive. So we have here the nuclear pores and here the actin. Okay, now let's move to the other channel. full separation. Okay, in these two channels, you can see the color imbalance is not as important as in the other one. We can still see the two dots. Again, same procedure as the other one. So this one is the booster barriers. So this is plumbing. So this is in magenta. So you can see it's a little bit more difficult because of this color imbalance. Okay. So now I'm going to separate the other one. And this one I wanted in green. So this is tubulin that you can see here in green. Normally, well, it's a little bit more complicated than that. Okay, so now we have separated our channels more or less. Now we're going to save the images. So this is tubulin 3. Okay. So this is the amine 3. This is not this image, but this one. So this is the actin. Okay. And this is the okay, this one didn't work. So. Let's do it again. I mean, I think I can make it work. Okay. Okay, I will just okay, how come the phasor plot line doesn't extend to the edges of the universal circle in this case? Okay, in this case, it doesn't extend to the edges because it means that your dyes have already a complex lifetime, meaning that they're not non-exponential. As I explained in the beginning, if the dyes itself have a complex lifetime, they will not be in the edges, but will be already inside the universal circle and not on the edges. That's why this is the case, that it doesn't go all the way to the edges. So we have already complex dye. Why did I draw a shorter line for the green channel? Or which one? Or this one, yeah. One, yeah. I draw a shorter line because I see that there is starting to see some crosstalk about it. But yeah, I'll say it doesn't. I wanted just to take out most background from the nucleus. That's why I wrote it. That's what I did, that shorter line. Just actually by controlling this, the length of this line here, you can see that I can more or less take out or not the background channel. That's what I did it. Higher intensity data. Can we get a radiation frequency? Intensity-based data, so frequency data out of this. So the problem is that when you do a phasor plot at any FLIM analysis, once you do the processing, you kind of lose the intensity data in it. Because what you're doing is that you're taking the photons and then you're just distributed it in different parts. So that is actually quite, so it will be quite difficult to do any frequency data out of the images. Or if you will need to do it, then you will need to do some internal control to make sure that the unmixing is not damaging. I would say it's not changing a lot of the intensity data. But I would say it's the same case with any unmixing algorithm. You're already separating, so any intensity-based data, you might lose them. Yeah, that's true. The reproducibility, I say, it looks cool, it works, but I mean, as with every experiment, you need to run some controls because normally you know what you're labeling. At least I hope so. I haven't really seen people that label structures that they don't know and they don't know what to expect. So this is, for example, if people want to label actin plus, I don't know, tubulin plus other things, so you already have a rough idea of how the structure looks like. So you have that internal control, and then you can do other internal controls just to make sure that the mixing that you're doing is quite capable. And as some person mentioned it earlier, maybe in the future you can make one machine learning algorithm that will be able to give you something stable and less empirical as this one.
So in a sense, these samples that Mariano showed, these are the controls because we know how actin looks like, how nuclear pores look like, and what pattern we can expect. It's getting, of course, more difficult if you have like 12 different surface markers on the surface of some lymphocytes, where they all stain the plasma membrane, and then it's your guess whether you actually can see different ones or other ones. So if those dyes really should co-localize on the same structure, then it's getting more complicated. And in particular, if you don't know how these structures should look like.
Yeah, exactly. Okay, so now I have some some overexposure. Okay, so okay, you get the values about the radius. Would it make sense to use the same settings for different image? Also, I would say it will depend also because then you will also have, for example, autofluorescence contribution from other parts of the sample. So it might make sense in the same sample. I think you're totally right with it. But I think you should, in the beginning, do a case-by-case scenario, and then I think you can just apply it, just copy-paste different rows, and then try to see how it is. But I don't expect the lifetime variation to be big within one sample. So chemical observation. Yeah, exactly. Everything can change the lifetime of your sample. That's a very good comment. pH, vesicle release, oxygen. So that's why in this case, the phasor approach is also very interesting because I'm not focusing in determining the exact lifetime because I know that anyway, depending on the sample, it might change. That's why, for example, if I do a control and a pattern and say, okay, this dye in this cell has this lifetime, and then I label the same cell but a different structure, the lifetime will change. And then all the controls and all the patterns that I did will be not useful anymore. So that's why here I'm just focusing on the differences to avoid having this problem. Exactly. So this is what I said. The aim of this workshop is just to show you that we can discriminate different colors using the phasor. I just said the only interesting thing that we want here is just to use the lifetime to differentiate structures. We don't want to know the lifetime of the dye. So that's why in this case, the absolute lifetime is not as important as the other ones. So this is the cell that I obtained here, but it's kind of overexposed because of how sometimes Leica have the settings. So I hope we'll have a very, outside there will be an update with a easier way to export this data. But of course, I also have acquired some other images that are kind of better. So you can see here the tubulin in magenta, in green is the lamine, the actin in cyan, and in red the nucleophores. And you can see that, okay, as I say, it might be not, I would say, some empirical, some reproducibility difficulties, but I think we can obtain really nice results with these images. And the most important thing, with not so much effort investments, because in this case, I mean, it's like a fax play. It's like I'll say, you can play like a fax plot. So you can just choose areas and you say, okay, this area corresponds to this one. And it is completely empirical, but hey, you're mostly interested in the difference. And in this case, it works for me. I think it's good enough. And I have other cell lines here. This one was a little bit more tricky because the labeling is not as perfect as I would like to, but still works nice. And even with low photon statistics, okay, the image doesn't look great. As I told Matt, maybe some deconvolution could work. But you can see here, and this is something that strikes me, is that we can still see, for example, the actin going in and inside the nucleus and all these actin fibers here. So I think with this phasor approach, we'll be able to differentiate. Okay, so I'm leaking some questions. Can this analysis recommend? Okay, so PicoQuant has other types of component separation, but as far as I know, they don't have a phasor plot phase analysis. So I think so far it cannot be done, because the aim that I did this workshop is to be able to do everything on phasor analysis, because our aim here in the facility is to be able to tell to people, okay, you can use these two dyes together and you will be easily able to separate them by yourself, meaning that they will need little to no introduction by ourselves, and they will be able to do their color separation themselves. So yeah, so I think you can ask the question tomorrow, because tomorrow I think people will have their talk. So you can ask me how for the color separation, because I'm not up to date with it, I'm sorry. Okay, regarding the effects. Okay, so this is how lifetime can be used to separate your colors. And for now, we are trying to implement more and more colors. So for now, we have just two channels. So the red, the far red, this is kind of the orange, but we still have the green channel available. So now we will be working to find the two dyes that we could use in the green channel to separate. And just now with three channels that people usually use, which are the green, the red, or the orange, or the red, and then the far red, and we'll be able to have 6 different dyes combinations to be able to do 6 colors.
Mariano, there was one question from Hella. Can you save and recall the phasor settings for analysis?
Yeah, I think, I mean, when you save anyway the data, it saves itself. So for example, now if I click save, it will save all the draws, all the rows and all the things that you have done here. So you can always come back and do them. For example, I did this, I'll say this project here, I did it beginning of this week or last week, just already to prepare the workshop. And if you go to the FLIM image, you can see all the rows that I did already, and then already saved.
So can you extract these data and apply it to another image? Or do you have to do it manually?
This is something that maybe you can, Daniel, is it possible or not? Because I haven't done it, to be completely honest. I haven't done it, so this will be.
I would also need to check. I don't know this by heart, sorry. But okay. As you say, if you save the experiment, it would save also all your analysis that you have done up until this point.
Okay. Yeah, so there is the answer, but yeah, I would say depending how many images I can assume you have, I can assume that you most likely copy paste all the rows that you have. So you don't want to start always from the beginning. Okay, if you publish data using a mixing by FLIM, what settings you need to report? That's a very good question. So if you unmix data by FLIM, I think the most important thing is just to mention the repetition rate of the laser. And then and also the kind of laser you're using, of course, the kind of laser, the repetition rate. And more or less the ROIs that you're using. For example, in this case, for this data mixing, I will say, okay, maybe this one is easier. Okay, for this one, I will say, okay, I use a linear gradient from 1.5 to 3.5 nanoseconds in the phasor plot, and then explain how you do this lifetime filtering. And in this case, with this information, for example, I will be already able to do some reproduction. But as I said in the beginning, the problem is the same thing with every unmixing, let's say, even a spectral unmixing analysis, right? The frequency of the phasor plot. Yeah, that's true. Yeah, this time domain, there is no frequency involved. So yeah, but as settings to report, I think you will just need to set in the lifetime edges that you used for your gradients, that you're using a linear gradient. How do you choose them? And then I think it will be good enough. Unless I'll say, and you can also add, for example, some unmixing data to see how it looks like. But yeah, at least I think this unmixing results here, for example, with this sample, I was really impressed because this mitochondria is really very difficult to see, very filamentally. I mean, it's very, very difficult just by the eye to separate them. But here with the phasor, with no, let's say, fitting or no other input or many variables, I'm just able to differentiate them very quickly. And of course, if you're worried about the controls, you can always stain the dyes. I would say you can stain the same cells with just one dye and just compare how they look like, see if it works well. So you have any other questions for the unmixing? If not, okay, then something that I can also show you is that we can also do this with autofluorescence, because this is something that we haven't really done it so far. So we have only used lifetime to separate different dyes by autofluorescence, but you can also use autofluorescence itself of the tissue to add some contrast. So for example, this is one tissue sample that has been prepared by one of our colleagues here. So this is a submandibular gland. Submandibular gland that it's labeled with astral blue and with Erken rot, and with a red label that labels basically the nucleus of the cells. And I just put it under the microscope and turn on the multiphoton laser to see what contrast can I obtain, and obtain this very nice lifetime image. And you can see here with the different colors is that blue is the shorter lifetimes, and towards the red are the longest ones. So in blue here, what you can see, these are the erythrocytes. So for example, here we have some veins, small venules. Here, this is apparently an artery. I can see here, hence the thick muscle. There is another vein here. And maybe this will be easier. And this is interesting, here you have a small vein, and I think this is also a small arteriole, just because of the thicker wall, muscle wall that we can see here. What you can see in yellow all around is the collagen. The fiber. And oh yeah, I forgot to mention this. This was detected with the dye detectors, and the excitation was at 850, 860 nanometers. So this is another image from the same sample that we can see here. So again, the collagen yellow reddish, the erythrocytes and all the vascular, the erythrocytes in blue, very short lifetime. And you can more or less also see the membrane of the cells here, big membranes, yellowish. But sadly, with this excitation wavelength, we cannot see what's inside the. I'll say, did I speed the image? Yes, because as you can see here, the scale is 250 microns. So, and it was a thick sample. So I did several fields, and also I did a stack because I wanted to have also all the stack of the image. So again, this is this. And then I decided also to turn on the, how long did it take? Ooh. For the big one that I showed in the beginning, I think it took me, 1 or 2 hours. Because I would say it's basically, how many tiles? I think it was 30 tiles, 35 tiles, and a stack of 5 Z stacks, a Z stack of 5 per position. So in total, it was a huge amount of. So it really took me a long time, but I think the result is mostly worth it. So before it was just a multi-photon image, and now I turn on the 488 laser to see how it changes, and then you can see that now I can see the contrast inside all this group of cells. So again, collagen is still red. The erythrocytes, however, have changed in lifetime. So with this excitation, the lifetime is a little bit longer, hence they're greenish. And all the cells here compounded that you can see inside are bluish. And this is one of the nicest images that I have obtained. So this is just a sum up. So this is a very small tile scan, so it was not really long. And the nice thing is that here you can see the membranes of the cells and also the nucleus of all these cells that you can see here, together with the erythrocyte that shows a very nice rainbow color, collagen again in red. Something that also interested some. We showed these images to specialists in histology, and something that they really, I think as far as I remember, like it, is that you can even see the erythrocytes in the collagen just because of the different lifetimes. So all of these cells here inside the collagen, because of the lifetime contrast, we are able to see them. And okay, you can also see the nucleus here in this group of cells together with the collagen. And yeah, I will say just to show you that just with normal autofluorescence, you can just play around with the phasor and with the with the natural autofluorescence. And even as I told you, this one has histology dyes, and this is a very old slide. I don't know how many years old, but it's quite old. You can still do some. You can still add lifetime that will add you an extra contrast to the image and maybe extract more information. That's it here. So I will just show you quickly how it is because I have the slide here. So I will be back soon.
So it turns out that most classical dyes used for histology, they are also fluorescent dyes. For example, eosin used in HE staining, hematoxylin eosin staining. The eosin is very nicely fluorescent. And with lifetime, you suddenly see a lot more differences in the sample that you usually would expect. So if you should have a lifetime microscope around and maybe some classically stained dyes, just give it a try. You might get wonderful images. And I think not a lot of people have ever tried applying that because they lack the tools. So classical histologists usually do not have a FLIM microscope around. But people with a FLIM microscope might just get a classically stained slide from some other department in the neighborhood and just try it for fun. Maybe if you have the stitching capability, so if you have like a motorized XY stage, you just might want to give it a try to let it run overnight. Make sure that nobody switches on the light in the meantime, because that happened to one of us. We might get nice results. So H&E staining, hematoxylin, as far as I know, is not fluorescent, but eosin is. So that might also give some nice results. That's actually one of the things we want to try, but eventually with these kind of things, where you do not have a direct application, you run into manpower problems very, very strongly. This is not an HE staining. This is a different staining. If I get it right, Sonja, help me if you're there. If I get it right, it's Astralblau and Kernecht Färbung. That's what it's called. So this is not an HE staining. HE staining might look completely different, maybe even boring. I have just no idea because we didn't try yet. Yeah, they look totally great in my eyes. That's also why I have this as a background picture, the one in particular here. It's kind of, I said to the histology person, it's kind of a solution in a search for a problem, because we can see a lot of details. We have no idea whether this might be of any interest to histologists yet. But maybe if you have a good connection to one of those departments and you have a FLIM microscope, maybe it's just worth a try.
So maybe during the time Mariano is still searching, I could share a few numbers with you. I have 2 slides.
So I'll just kill Mariano's.
Just for, so sorry for no, oops. Can you see it?
Yes.
Yes, okay, so we go to the presenting. No, okay, no, we have to switch it. Okay, okay. So that's just to give you an idea about numbers, what can happen to your fluo force. Yeah. So that's Atto 488, and you start maybe in water, and that's maybe the expected lifetime you might have in mind if you choose it for the separation. But what can happen is that you end up with something that is 2.2. This is after attaching Atto 488 to IgG molecule. A fixation step using methanol, what could be needed for some of the antigens, and then storing it in just Mobile. So we always, in the end, avoided any DAP4 or any other anti-fading, because that will, and on top, quench heavily. And you see everything gets really multi-exponential because of the complex environment that was mentioned many times. This is just, yeah, to share a few numbers with you, because we investigated this a long time ago, 10 years ago. And that might be different also for different dyes. So Atto 647N is not that heavily affected. Yeah, that's just a smaller reduction in lifetime. That's the only thing that I wanted to share with you.
That was cool. Thanks, Shafi. Okay, so now we'll see one tissue, see how it looks like. So I will just take.
Mariano, you have to restart the screen sharing. I stopped it. So that Steffi
Yeah,
can
that's
show the
true.
slides.
No, it's true. It's no worries. I'm just anyway trying to do some calibration. Okay, let's start low. Then we'll see what we can see. Sequence, no more sequence. Oh yeah, of course I need to use the dye detectors. That will be nice. So one nice thing about this system is that the NDD detectors are also spectral. So it's really the no filter life It's really amazing. Actually, what I could do is that, yeah, I will say there is some collagen. I will try to do some SHG. Because I don't remember how it went. Okay. Big area. So apparently I don't have collagen, or maybe. Oh well, it was mostly a try. Maybe I will find another place. Okay, so now I have my detector here. I have my tissue sample. Of course, it's very thick, so I want to navigate. We need to change this. Okay, that is more like it. Okay, you can see it's a very, let's say, thick sample. Hence what it took me some time to do the nice image that I showed you. Okay, so this is, I will say, the normal, boring focal image. Okay, I'm saturating a little bit. Not much. Okay, that's nice.
So it's not really confocal, it's a two-photon excitation image. So, but nevertheless, it's just a boring image. Yes, I agree.
Yeah. Okay, so now we'll just take the image and let's see. Okay, so here we can see the normal intensity one, and here now we'll focus on the fast FLIM one. For now, we'll see. And one interesting feature about it. Oh yeah, I forgot to change the resolution. Wow. But at least you can see, for example, here that just with the lifetime here, you just see some structure, but you know that there are cells here. But when I turn on the FLIM, you can already see the nucleus cells. So I will just increase the resolution in the next image. Well, you will need to believe me, these are cells. And this thing, this label in blue that shows short lifetimes is the cell nucleus. That you cannot see it with an intensity-based image. Okay, I will just stop it and increase the format. You know, let's make it bigger. Nice. Okay, let's go. A comparison of H8 versus H8. I think we can, I don't know if we have the image, but we can definitely send you, because this we have the raw data, the FLIM image that we have, and also the normal fluorescence ones, just to see what you can do with the extra contrast that FLIM gives you. And send the question, can you simply make content quantification area using such an image? I don't know what you mean content classification, but I would say we're giving some contrast, for example. So as I showed you already earlier, so here, just by turning on the FLIM, we can already see the nucleus. So if you want to determine the nucleus area, then yeah, I will say you can. But this is also really a really nice sample just because of the staining that goes to the nucleus. That's okay, you can more or less see it now, but it's not as evidence as the neutron. And this is 2-photon excitation for now that I'm doing. Okay, so I did have some collagen. Aha, how does it look in the phasor? Here it is. So here the phasor has changed because we're using the MP laser. So the MP laser is at 80 megahertz, hence the shorter resolution, let's say, of phasor plots. But yeah, once the image finish acquire, we can maybe play around a little bit with it, see what we can get out. Okay, maybe I will just stop it now. Of course, I can always stop the measurements. If I wish, I will turn off the detectors. And did I acquire some? Oh yes, you can see here. I also got some second harmonic, so you can see here the collagen labeling. Looks cool. And you can also add extra contrast to your tissue. Okay, so now with the phasor, what can we do? Okay, maybe I need to switch to this one. Okay. So maybe I can just switch it a little bit. So as you can see, most of the contribution comes from the collagen for the long lifetimes. You can see here. And then we have very short component that corresponds to the nucleus of the cells. So after with this, depending, so since you have another layer of contrast, then you can just export this image and do some analysis for it. And I haven't really tried to do some autofluorescence filtering, but let's see what happens if I just try to say, okay. For example, here what I'm trying to do is like, okay, I just want the collagen, which, or let's say the big structures, which doesn't look that bad, I would say. Maybe I can just decrease the harmonics in this case, because I'm not using, okay, yeah, it's better like this. You see, in this case, the resolution was too high, so I just needed to decrease the harmonics a little bit. So in this case, it's more or less complicated, but you can see that I could technically more or less isolate the collagen in this case, or I could just take it out. For example, here I just want to see the nucleus. And here you can see, hey, I just want the nucleus of my cells, hence only the nucleus. So this is the original image, and this is the FLIM image with only mostly the nucleus. I mean, you have still also some short components, but I think this is already, let's say, a good tool if you want just to observe this one nucleus quantification. Of course, you will need to add some post-processing to it, but I think it looks pretty cool to be able just with lifetime to go from this image to this image, where they're just interesting in the nucleuses. Okay, so far this is everything that I wanted to show you.